Okay, and then we'll discuss that as well. Okay, so I'm going to cover tonight all the materials from the beginning of the semester up until now, sessions 1 through 5, material that's likely to be on the exam. As I go through it, I will give you some feedback on what I think is likely to be on the exam. I'm going to kind of go through this in the order that we probably were exposed to it, but probably not completely. So don't get too worried about that. But I want to cover certain modules that I know that perennially are issues and that are important things moving on as we go on past the exam number 1. So any questions on that? Somebody type in that box just so I know you're still there. Okay, good. Here's a good thing. Okay, great. I'm going to go ahead and get started. And the first thing we covered this semester is something that will become clearer and clearer as we move on through the semester, why this is so important. And that's variable types. Okay, so as far as variable types are concerned, right, the main ones, the ones that we see in SPSS, the main ones that we see in SPSS are nominal, are scalar, and ordinal. Okay, and obviously nominal is a name, right? Or a lot of times you'll see that described as categorical. Okay, and you sometimes may see the word dichotomous used along with that. Okay, I misspelled it there. Hang on a second. Dichotomous. Okay, you'll see that word used as well. Dichotomous means it has 2 values. So you can have a nominal categorical variable like hair color or something of that nature, or room number, for instance. It describes a name. It names something. Ethnicity, for instance, is a nominal or categorical variable. When that variable has only 2 values, such as male, female, ill or not ill, diabetic, not diabetic, that's called dichotomous. And we know that we dealt with that a little bit differently because of the binomial distribution. There's ways that we can analyze that numerically in certain cases. Those are basically what we're looking at in that category of variables. Now, you could argue that this other variable, ordinal, is also a kind of category. Ordinal is a nominal variable, a name that has, in its nature, has order. Anybody want to suggest something that's like that, that might be an ordinal variable? Temperature's a number, right? So if you were to say temperature, low, normal, high, that would be ordinal, right? That variable would be ordinal. But if you say temperature 98, 99, 100, 101, that's numerical. Okay, so the idea is that, for instance, when you fill out a survey and the choices are poor, fair, good, excellent, that rating is a ordinal variable. They're names, fair, good, but they have some sort of relation to one another. Okay, the pain scale 1 through 10 is an ordinal variable. The 1, 2, 3, 4, they don't have a specific value. Like there isn't something you can quantify like pain level 3 represents, because it's different for everybody. But you know, if somebody tells you, well, pain level now is 3, but you know now it's 5, you know that's greater than the 3 was. You can't really measure how much greater, but you know it's above that. When you get grades, A, B, C, D, F, when you get grades, that's an ordinal variable because they're letters, but the letters represent an order, right? So those are ordinal variables. They're nominal, but they have order. Okay, and then finally you have scalar. SPSS uses the word scalar. In most places, you'll see numerical, right? So numerical is anything that contains a number. Temperature, blood pressure, weight, BMI, and so on and so forth. Okay, so let's go through a few of these. Gender, what's your gender? What kind of variable would that be? Dichotomous, nominal variable, right? Nominal variable, which is also dichotomous. Nominal dichotomous. Okay, what about hair color? Bingo, exactly. Okay, what about blood type? Bingo, exactly. Yeah, a lot of these are going to be nominal, right? Especially in surveys. What about how much you weigh? Scalar or numerical, same thing. Okay, what about ethnicity? Bingo. Okay, now let's get somebody else a chance to answer here. Were you born in the United States? That's often called nativity. The answer to that question is somebody online? Nominal, right? It's nominal. What special kind of nominal? What is it? Right? The answer to that question, dichotomous, exactly. All right, that's another dichotomous. How old are you? Right? Well, age again is numerical or scalar. What about blood pressure? Okay, numerical. I'm going to add one to here. Have you ever been told you have high blood pressure? What kind of variable is that? You think?
Nominal.
Nominal, right? What kind of nominal? Yeah, exactly, because the answer is yes or no. How many cups of coffee did you have today? Numerical, okay, numerical. Now, very frequently, we qualify small numbers that are integers, such as how many cups of coffee you had today, because usually people don't drink 10 cups of coffee in one day, right? Or how many siblings do you have, and so on and so forth. We have a special name for that. Anybody remember what that name is? Somebody want to take a guess at that? We call that discrete, right? They mention that in the textbook, I think. That's a discrete numerical variable because it has an integer value and a low number. That's a little. I don't like. I'm not in love with using that particular one. Who knows? Maybe I'll try and avoid that on the exam or something like that. Now, if instead of asking how many cups of coffee did you drink today, I asked you what is the average number of cups of coffee you drink in a month, what would that be? That would be numerical, right? Because that's going to be like, I can't get that in the end there, I guess. Just put an end there. It's going to be numerical because the average number is going to be 13.7, 42.8, 11.1, and so on and so forth. It's clearly going to be a number on a number scale. The other characteristic of scalar and numerical variables is that they're on a number scale, and the differences between the numbers have some meaning. Like in other words, a blood pressure of 80 is 10 millimeters of mercury than a blood pressure of 90. It's 10 millimeters less than a blood pressure of 100, and so on and so forth. Where when you're talking about a categorical variable, when you're talking about a ordinal variable, like I had one here, didn't I? Lost it. When you're talking about an ordinal variable like the pain scale, the difference between 2 and 3 might not be the same as the difference between 3 and 4. So there's no way really to measure that. That's why that's an ordinal variable, even though it's described as a number. Okay, so why is this so important? Well, the reason why it's so important is going to be the next thing that we're going to do. We're going to take a look at SPSS and applying SPSS to organize data and summarize data, produce what we call descriptive statistics. Okay, so what we've done here is we've downloaded from Blackboard a series of files. And I'm going to just open up one of those files in SPSS. And let me see what I have here. Okay. Let me just see what's in this one. Okay. Which one do I want to work with? I'm going to open up this. There's one called CHS 2013. That stands for Community Health Survey in the year 2013. Okay, that's a survey that New York holds every year. We're going to be using that or working with that later on in the semester. So I'm going to go ahead and open that up. Two ways on your machines you're likely to be able to open it up. If it installed properly, if you're lucky and installed completely, you can double click on the SPSS file, which is a .sav file, and it will start SPSS for you. If you're not that lucky, you can start SPSS your own. Go to your programs file or go to your start menu, tell it to start, go to programs and tell it to start SPSS. On the Mac, we can use shortcuts on the toolbar down here, or on the PC, it might be on your toolbar as well, or on your start menu from having used it previously. And we get a little opening screen. Then we get a pop-up, an introductory window. I actually started it twice, I think there. Get an introductory window which will allow you to open a new data set, so on and so forth. And you can work from that window, or most people don't bother with that. They get rid of that and they just let it open up an empty file as it's done here. Okay, and there's nothing in here right now. So I want to work with an existing file. So I'm going to go up to File, Open, Data. I'm going to navigate to the desktop. Okay, let me go to my desktop. I'm going to click there. I'm going to go up to desktop. On the PC, it might look a little bit different. And I'm going to look for my SAV files. They're going to be in my folder. I put them in a folder. You might have them on your desktop now. Oops, wrong session. Okay, here's my community health survey. I'm going to click open. Okay, it opens it up. It brings up the output window briefly and types in if there's any warning about issues with the data file, the type of encoding. You might see this pretty commonly on here because there's several different ways that files can be encoded on SPSS, and there's some older versions of these files that might be coded a little bit differently. Okay. Okay, so we opened SPSS and we're examining it now. And we have, in the columns, we have variables. In the rows, we have cases. How many cases do we have here? Well, I can scroll down to the end here. Let me make this a little bit smaller. I can scroll down all the way to the end here. And I can see that I have 8,698 cases here. That's how many people were covered in this survey. Okay, so I also can see that there's numbers in here. These values, the values that they got in response to their survey are recorded as numbers. So for instance, Demog 1, I happen to know that that represents the age of the age. Okay, so in order to make sure that we understand that it's age, I'm going to go to the variable view. The variable view just summarizes the different variables that we have. So naturally, since we have 10 variables, you're going to find 10 lines here. I'll go back to the data view. You'll notice that there's 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 columns here. And those 10 columns are represented by rows in the variable view. And this first one represents the answer to the question, what is your age? I'm going to make that a little simpler. I'm going to just go in there and I'm going to change that to age. Okay, what's that going to do for us? What that's going to do is from now on, instead of using the variable name demog1, demographics 1, which they used in the survey, it will, when we create a chart or a table, it's going to change that to age, so it's just easier to work with. Okay, the next thing we see there is borough. Well, now you see that's borough of residence. So I'm going to simplify that a little bit and call it borough of residence. Okay, so I'll wait for you guys to catch up on that. I'm sorry? Oh, just click into it, right into the label. Just click into it, double click into it, and it should let you edit it. Right? If you just click once, it highlights it. If you click the second time, it should let you edit it. Okay, borough of residence. Okay. And I'm going to do one more because I think I'm going to want to work with one more, and that is I'm going to do uh, I'm going to do insured, and I'm just going to change that to, let's see. Actually, I'm not going to do that. I'm going to do gender. I'm going to use sex and just say sex, male or female. I'll just leave it the way that it is, and we'll work with it the way that it is. Okay, so now age, you'll notice that if I go back to the data view, the age, that first column is the actual age in years, 57, 64, 28. As it happens, they don't interview anyone under 18. So you won't find anyone under 18 here. But you'll find every other age group in here, 61, 65, 31, so on and so forth. Okay, so that's a numerical variable. Okay, so if I go to the next column, borough, you'll notice that there's numbers there. 1, 2, 3, 4, 5, so on and so forth. There's 5 numbers. Obviously, each of those numbers represents the borough that that person is from when they interviewed, borough that person lives in. So now we're not going to, when we produce a table or a chart, under borough, if we display something that says borough, a 1, 2, or 3 is not really going to describe to the person looking at that chart what borough that is. So we want to tell SPSS what those numbers represent. So we do that in the variable view. And borough is a nominal variable. Brooklyn, Queens, Staten Island, so on and so forth. Right? It's a nominal variable. So we go over to the values column. We click in there. You'll notice that a little gray box opens to the right of that. You can click on that, and now you can start to add values for the borough. You can tell SPSS what 1 represents, what 2 represents, what 3 represents. Now, the information as to what on this particular survey, which borough was number 1, 2, 3, 4, is in a code book. It's in a book that describes each variable and tells you, well, if the person's from Brooklyn, put in the number 1. If the person's from Manhattan, put in number 2, and so on and so forth. For the moment, we don't have that. I don't want to go searching around for it. So we're just going to assign, we're going to make believe that we know what the values are. So for instance, I'm going to say 1 is the borough Manhattan. And I'm going to click add. Now I'm going to tell it the number 2 is the borough Queens. And I'm going to tell it the number 3 is the borough the Bronx. And I'm going to tell it the number 4 is the borough Brooklyn. Okay, click add. I'm going to tell it the number 5 is Richmond, which is the proper name for Staten Island. Okay, so now SPSS at this stage, when I click OK, now SPSS knows what those values represent. Now, the other thing I'm going to use is gender. And similarly, gender is also a nominal variable, except that gender is what kind of nominal variable? It's dichotomous, only has 2 values. So I'm going to go over to our values column. I'm going to do the same thing. I'm going to click into the values column, get that gray box, click into that, and I'm going to tell it that 1 represents, before I do that, let me look at the data. If I look at sex, the numbers are 1 and 2. I don't want to put a 0. I don't want to put that female equals 0 or something like that because there are no zeros there. So I'm going to click into that gray box, and I'm going to say the number 1 represents female. Click add. The number 2 represents male. This is called coding. Okay, really, I would be doing this with the code book by my side. So as I tell SPSS what these things represent, I will have some documentation that I actually know what they are. So make sure you click add after you add the last one, or it won't take, and then click OK. So if I go back to my data view now, okay, go back to my data view, you'll notice that you can see that the borough is represented here by the name of the borough instead of the number that was typed in. And you can see for gender that the gender of the person that row represents is now indicated as male and female. Did you click add? Oh, okay. One more thing. At the top here, up in this menu view, right? If you look up at the menu view, there's a number of selections up there that you can select from. Grid lines, leave that checked off. These are toggles. Each time you hit them, it changes. If you go over to value labels and it's not checked, it means that SPSS is not substituting the value you put in there for the number. So if I turn that off, you'll see that the numbers are there. I don't see the gender. If I go back and click it back on, now I'll see the gender. So if you did you give that a try to come back? So that's the reason why you didn't see it. So keep an eye on that toggle. By the way, you can click between the variable view and the data view by using tabs on the window, or you can also go up to view and toggle there. Right now it says, oh, let's go to the variable view. Let's change to the data view, and so on. Okay, so now we went through this whole thing where we were so concerned about what the data types were. And I'm going to highlight this first one, age, and we know age as a scalar variable. Notice SPSS chose scalar for me automatically. It shows a little ruler as a symbol to represent a numerical or scalar variable. Why did it choose that? Well, it saw the numbers were 18, 72, 73. It interpreted it as a scale. It doesn't always get it right, so you have to keep an eye on SPSS. As far as Burrow is concerned, it recognized that as a nominal variable, right? Because it only saw 5 values, 1 through 5. So it figured it's probably more likely a nominal variable than a numerical variable. And it also noticed that there were only 2 values for sex, so it automatically assumed that was a nominal variable also, which it is. Dichotomous, but it's a nominal variable anyway. Okay, so we're going to work with those 3 variables that we have here. I'm going to first work with categorical variables. Okay, dichotomous or categorical, whether dichotomous or not, categorical or nominal variables. So now, how do we organize that kind of variable? Okay, well, we don't want to take the average. Average, if I talk about gender and I have 100 people and there's 45 are male, 55 are females, there is no average. There is no average person. They're either male or female. If I know their ages, I could find the average of their age. So averages are used for averages, standard deviations, variability, variance, box plots. Those are all things that we use to describe numerical variables, a collection of numerical variables. Categorical variables we describe differently. Usually we describe them by frequency. How many females, how many males? We plot them as bar charts, the height of the bar representing the number of people that are male and female, for instance, or live in this borough or that borough, and so on, how many boroughs we're working with. So in most cases, with nominal or categorical variables, we're going to be looking at frequencies with bar charts, not histograms, bar charts, and sometimes you might see pie charts that are interesting as well. So how do we produce these kinds of statistics in SPSS? So let's see. I'm going to go to Analyze. Okay, almost everything we do in terms of doing an analysis. I noticed you guys have given me some feedback online, so I appreciate Angelia. Thank you. We go almost always as we proceed either go to analyze or to graphs to produce output that we're going to use in, say, a report or a paper or a journal or something of that nature. Later on, we're going to look at other things like transform and data handling and so on and so forth for manipulating the data so that we can do some more things from it with it than we were able to with just the raw data that we got. But for right now, we're going to be primarily interested with analyze and graphs. Those are going to be our domains for the next at least week or two, right? Before we get further on. So I'm in fact pretty much the rest of the semester, that's where we're going to spend most of our time. So let's take a look at analyze. Analyze, first thing that comes up is reports. Okay, and if you have a code book, if code book buried into SPSS or that you can access, you might go into there. I wouldn't worry about reports for right now. We'll get back to that at another time. We're going to go past that. We're going to go to descriptive statistics. Okay, so now, as I said, when we're dealing with categorical nominal variables, we're mostly interested in counting them. How many people have brunette hair? How many people have blonde hair? So on and so forth. Not averaging and things like that. So I'm going to go to descriptive statistics and frequencies. SPSS opens a window and it realizes that we have a number of variables that we're working with. So in order to tell SPSS which of the variables that we're working with now, we have to actually go in there and we have to click that variable. Okay, so I'm going to go into gender for starters, sex. So I'm going to move that into the variables box. Now SPSS knows that's the variable that we want to work with. Okay, so now at this stage, I have to say to myself, well, what do I want to do with this anyway? Well, I'm going to click on we have various options here. And notice that there is numerical variables here. So if I click on statistics, I'll see a lot of things here, mean, median, quartiles. Those really apply to numerical variables. So I'm not going to bother to select any of those. Okay, if I click at the charts, I see, oh, bar charts, pie charts, histogram. Well, one of those is something that I don't want to choose, right? I don't want to choose histogram because histograms are for numerical variables, not categorical variables. But I might be interested in seeing a bar chart or a pie chart. I'm going to click pie chart. Now notice as soon as I clicked one of those, it filled in one of those radio buttons down here, chart values. So you can display, I'll start with bar chart for starters. You can tell it you want the bar chart to display as a frequency, the actual count of people, or as a percentage of the people on the y-axis. Okay, I'm going to click frequencies for starters. So now it knows it's a nominal variable. It knows I want to create a chart as well. So I'm going to click OK. When I click OK, SPSS is going to open a new window, an output window. All of the output results will go into that window. And that window builds up like a ticker tape. In other words, the next analysis we do is going to be underneath the one we did before, and the next one, and the next one, and the next one. So it's only almost like an old adding machine when they have the paper tape and so on. So it's all going to stay there until you close that window. So I'm going to click OK. The output window will open up, and it'll give us the results of the analysis we asked for. So let's take a look. Descriptive statistics, it tells us that there's 3,740 females, there's 4,958 males. Well, the females represent 43%, the males represent 57%, and so on and so forth. The bar chart that we have, notice that the y-axis is in frequencies. The 3,700 females and was it 5,000 or just under? Just under 5,000 males. We can see relatively how many people there are in each group. Okay, you can actually, just so you know, we're not going to do anything with this right now. Just so you know, you can double click this, open it up, and you can edit this. You can change colors, you can edit the text, and so on and so forth. So there is an editor that you can get to by double clicking. I'm just going to close it again. Notice that when I click on it, you get I was going to say running ants. You remember the old graphics programs where you get these little dots that would walk around the picture when you selected it, right? The artists usually used to call those running ants, but actually just draws a little box, a thin box around the chart or the table. So I'm going to click on this table, right? Now that I've clicked on that table, I can say copy. There's a couple of ways I can do this. I can go up to edit and say copy, or I can just say Command C on the Mac or Control C on the PC and copy that into the imaginary clipboard. Then I can go to Microsoft Word. Okay, and I can go to Microsoft Word, open up a blank document. I'll wait for you guys to open a blank document up. No, just click it once and the line will appear. You'll see a thin line appear around it. That means it's selected. Okay, so even just a blank sheet in Word would be fine. matter of fact, I'll open up a blank sheet for myself as well. Is it working out for you? Hang on just a second. Let's see. I just want to get my 200% there. Okay, my battery is actually charging up. Oh God. Let's see. Just click on once. That's it. Now you can say Control C. It's copied. Okay, or you could have gone up to Edit and Copy. See, it does the same thing. Okay, so now open up Microsoft Word and say Control V. Bingo. That's it. That's all you have to do. So again, I'm going to do that myself here. Okay, and bingo, there's your chart is inserted into that Microsoft Word document. Similarly, I can go back to my SPSS output page, and I can click on and highlight that chart that I just created. And I can say Control C again, or Command C if you got a Mac, or go up here and say copy, and go back to the Word document, and now I can paste that image into my Word document. Now I'm going to hit paste here, and it's not going to work for me. I'll tell you why, because there's a bug in my version of Word here for some reason. And see, I pasted it in, but you can't see it. It's there, but you can't see it for some reason. So I wind up doing something weird, like copying, doing a screen capture and pasting it in. But it should work for you. Did it work for you? Okay. That's just a weird bug that I have in my version of Word. Okay, so at any rate, that's it. So in other words, if that was my question, I wanted you to produce this chart and this table, paste it into a Word document, then you could say save as, save the Word document. I'm gonna maybe it's problem number 7, and I might put my name on it just in case it gets separated, right? And save it to my desktop. And then when you're on the exam, you can say, just as you did in assignment 1, you can say problem 7. When you go to answer problem 7, there will be a upload button. You can click on the upload button and then navigate to the desktop where you just saved that. Make sure, oh, by the way, yeah, that's the other thing. Make sure when you say save as, that the place where it's saving it is on the desktop. Like I'm saving it on desktop. Sometimes it might save it to documents or some folder or something like that. Then it's a pain in the ass to find it. Make sure it's saving to the desktop or somewhere where you know you're going to be able to access it easily, right? So once it's there, on the exam or on the homework, you can say upload or attach document. Click on that button, navigate to that document, click it, and it will be uploaded. And that's it. That's really what we're after here. Now we're going to take this to the next step. Oh, by the way, just so you can see, I'm going to go up to Analyze, Descriptive Statistics, Frequencies, except this time I'm going to go into Charts, and I'm going to tell it, do it by percentages instead. I'm going to say, okay. Notice SPSS repeats everything. It did the chart again, so on and so forth. This time, it does it by percentages. So you can see that 43% of the population is women, and 57% of the population is male. So you could do it that way. You could also say Analyze, Descriptive Statistics, and Frequencies again. And instead of for charts, pick a pie chart. Okay, you don't see too many statisticians using pie charts, right? They're a little bit kind of primitive, but we'll click that, and bingo, there's your pie chart. So it's easy to see that there's more males than there are females in there. And again, you can double click into this. It pops up in a new window in an editor, but you don't have to do that. You don't have to worry about that. Okay, notice what SPS is doing here. It's adding all of these things onto the end of the last analysis. So this document is all being created in a manner where you can go back and take a look at whatever you've done before. Now, if you really get a lot of stuff, in other words, you have, like you've done 10 or 12 analyses, you can actually use this sidebar to navigate, to click, to go automatically to wherever that particular last analysis was. We don't have enough to really make a difference there. Okay, let's do the same thing for borough. Borough is also a categorical or nominal variable. So I'm going to go to Analyze again, Descriptive Statistics, Frequencies. So this time, I'm going to take, you know what I'm going to do? I'm going to leave sex in there because you can work with more than one variable at a time. Obviously, in this case, they both have to be categorical variables because I'm going to do an analysis only works with categorical variables. So I'm going to get borough of residence and move that in there. That's a categorical variable, right? Then I'm going to go with the charts and I'm going to go back to bar chart because it's going to look a really kind of weird. Well, maybe not. I could have done that. And I'm going to go to frequencies. That's the one I feel most comfortable with personally, just personal preference. I'm going to click OK. It's going to do that summary, that count, that frequency count for both these variables and do bar charts for both these variables. And it's going to add them onto the bottom. Here is our frequency count for gender. Here is our frequency count for population in each one of the 5 boroughs. And here's our bar chart for gender. And here's our bar chart for borough of residence. And you want to know something? I don't know what the numbers were, but which borough do you know to be the most populous? No. Oh, Brooklyn, I think. I think it might be Brooklyn, right? So my guess is that the highest bar is probably Brooklyn. Which one has the most area? Geographical area. Queens, yeah, Queens by a long shot, yeah, Queens. I think Brooklyn may be the most populous, and Queens might be the one with the biggest area. And which one's the least? Which one is the least population? Clearly the least one. So we got that one right, right? You know, I'm not so sure about this one. I think it might be Brooklyn, but we got that one right. So we guessed we got a little lucky anyway. So that's nominal variables. That's how we deal with nominal variables. Now let's take a look at what we do with numerical variables. We only have one numerical variable to work with here. I'm gonna minimize, either just move it out of the way or minimize it, right? And then the Mac, it's that thing. On the PC, it's that little narrow bar. I'll get this out of the way. I'm going to go back here. I'm going to go into my data view. And look, there's the demog one, which is age, really, right? That's my one numerical variable. If I go into variable view, you can see that it's a numerical variable, age. So now I'm going to go back to data view. Don't have to, but I'm going to try to do it that way anyway. Now I'm going to go up to analyze. And again, I want descriptive statistics. I want statistics will describe this sample or this population to me. So I'm going to go into descriptive statistics. I'm going to say descriptives. I don't want frequencies because I don't want it to count how many 33-year-olds, how many 34-year-olds, how many 35-year-olds. That's going to be so complicated and ridiculous that it won't be really contribute to anything. But I do want to get descriptive statistics, numerical descriptive statistics, so at least I'll know what the average age is. The people in this survey will know what the variability is, the standard deviation, for instance, and the variance, those things that we calculated early in the semester. So I'm going to go to descriptive statistics and descriptives. Okay, it comes up again. SPSS wants to know which of these variables you want to work with. Since I am working with, I need a numerical variable, I'm going to take age, I'm going to move it into here so SPSS knows which variable I want to work with. I'm going to click on options. It gives me options. So automatically going to calculate the mean and the standard deviation. They're very popular. It's going to tell me the minimum and the maximum. I want the variance also, let's say. I want the range also, right? Sum doesn't mean anything to us. So that's about all it's going to give me. So I'm going to click continue. Then I'm going to click OK. Bingo. What's going to happen? The output window is going to pop up. There's the output window. It's going to add the results to the bottom. I'm going to drag this up so we can see it a little bit. And what do we have? Well, again, there were 8,459 people that they surveyed. The range was 79 years, from 18 to 97. The oldest person surveyed was 97. The youngest person surveyed was 18. Again, they only took people over 18. The average age was 49.19. The standard deviation was 17.53. The variance was 300. We don't use that so much, but we know that the variance, the square root of the variance, is the standard deviation, right? So we see the standard deviation. What does that tell you? Gee, that tells you that I would expect 95% of these people to be within 2 standard deviations if it's normally distributed between 2 standard deviations below 49 and above 49 and above added to 49. So 35 below that, which I guess would be about 24 to 35 above that would be 78. So I spent 95% of people between those two numbers. But that's an aside. It's got nothing to do with what we're doing here. So that's our table for descriptive statistics. Now I can ask it to create a histogram for me. I don't want a bar chart here because a bar chart will give me just each age and how many people in each age. I want a histogram here. I want to group them into ranges of ages. So instead of just doing that and analyze, I'm going to go over the well, hang on a second. Analyze descriptive statistics, the descriptives, just to make sure that we don't have any options there. I don't see anywhere to do a graph there. Style, I don't see anywhere to do a graph there. So no, it doesn't look like there's any way to do a graph there. So I'm going to go to Analyze, Descriptive Statistics, and I'm going to go to the next option below that, which is Explore. Descriptives and Explore are very similar functions. They both are used for numerical variables. And so for this first part of the semester, this is all we're really working with is these three selections here on descriptive statistics, and maybe graphs if we decide we want to go there. Chances are you're not going to need to go to graphs because we're going to find out that there's ways for us to get it through here. So descriptives, Explore. I'm going to click on Explore. Again, comes up, shows me on the left-hand side all my possible variables I can work with. Then it's got more than one box. The top box is a dependence list. Dependent means the variable that you're really interested in. In other words, what you're looking to analyze. So I'm going to take age and move it into my dependence list. Okay, so I'm going to go down here and I'm going to look at these various choices that I have now. Statistics. Well, it's going to do, I don't really have many things to select. It just tells me I can select descriptives, which is what I want. So I'm just going to trust it for the moment to see what that gives me. Plots. Well, plots, I can get a stem and leaf plot. I can get, let me get a histogram. Let me ask it for a histogram. And then it's got some others. I'm not going to bother with those. It's just going to get, I want to see that histogram. And then I'm going to go into options. Anything I need there? No, that's only concerned with missing values and stuff like that, and so on and so forth. Now down at the bottom here, I can ask it to only produce the statistics box, the numbers, or to produce only the graphs, or to produce both. Typically, I'll leave it on both. I'm going to click OK, and I'm going to see what we got. Okay, I'll give you guys a moment to do that. Okay, and what did I get? I got a little summary of how many cases there were here and if there were missing cases here. And there were missing cases here. 239 people, or 2.7% of the population, did not give them their ages, right? So it was a little bit smaller sample than we had before. Still a gigantic sample. Okay, so what's the average age? 49.19. Same thing we got when we did it the simpler way, the descriptives. What's the 95% confidence interval? You guys, we started to talk about 95% confidence interval or confidence intervals in general. I'm not going to review that now because it really doesn't come up on this particular exam. I will mention that there is one or two questions about standard error, okay, but I'll get to that before we get done tonight. But I'm going to skip over the 95% confidence interval. Let's see, the median, the middle value is 49. The mean is 49. Does that suggest a normal distribution? Sure does, right? The normal distribution is symmetrical, and the mean and the median, middle person and the average are the same, and that's pretty damn close. Variance, we saw calculate standard deviation, we saw calculated before. The minimum was 18, 97 is the maximum. We have the range there. Now look, we have something that tells us the interquartile range. We're going to discuss that in a second, so I won't make a big deal about that right now. But we know that's the middle 50%, the range of ages that represent the middle half of the population, the 25th percentile to the 75th percentile. Okay, so let's take a look at our histogram. Well, here's our histogram. Each one of these bars represents a range of ages, right? It made a lot. These are called bins. Each one of these might be 20 to 22, 20 to 22, 22 to 24, and so on and so forth. And it looks fairly normally distributed. The only kind of thing that's weird is, gee, what happened to this end? Well, they only took people that were over 18. That's the reason. It really might have been completely normally distributed, except for the fact that they restricted it to people 18 and over. So that's what the distribution like. This is our histogram. We can produce this graph to visually get a feel for whether it's a normally distributed population, and it looks pretty normally distributed. The stem and leaf plot is just the same thing as the histogram, except we used to use those when we didn't have computer graphics. We couldn't display it as a bar. So if you look at this, this is just a histogram on its side represented by letters. You guys remember ASCII art? You old enough to remember ASCII art? Ask, I'm sorry, I can't help myself. Okay, up until now, I've been very careful not to diverse, not to get nuts. Just so you guys know, I think it's important you guys see a little bit of the history. In the old days, when we couldn't display graphics on computers, literally they couldn't display graphics, only letters and numbers. People used to produce artwork using letters and numbers on a printout. So, for instance, here's Einstein. Einstein's these are all letters and numbers. That's called ASCII art, right? Is that person's image is all letters and numbers. Or if you zoom in there, it's all letters and numbers, but it appears as an image because of the density of the letters and so on. Why do I bring that up? Because this is kind of the same thing. This represents everyone that is 18, between 18 and 20, right? 18 and 20, 18 or 19 years old. So how many people are 18? Yeah, one, two, three. What they did was they put the first digit here, 1, and then each person there that was 18 or 19 is represented by a number here. These are all the 18-year-olds. These are all 19-year-olds. 20 to 21, 20 to 24 are represented here. 24 to 29 are represented here, and so on. And it winds up making a histogram very similar to here, except using only letters to do it. Okay, so in any case, normally nowadays we just would worry about the histogram. If you want to put this into your document, if I hover over it, you'll see a blue line, right? But if I go over here and click on it, you'll see it gets that thin black line. I can say copy and paste and put it into a Word document and use it as part of a report. Now notice, anybody remember what the name of the variable for age was when we started? It was demog1, demographic 1, right? That was the variable name. If we had demog1 down here, nobody would understand what this chart means. But instead, because we filled in that value, that label portion of the variable view, we filled in that label and and changed it to age. Then demog1, when we produce a chart or a graph, SPSS automatically substitute age for that. Okay, so finally it produces a box plot for us. And let's go over what this box plot tells us. First of all, these things are called feathers. The thin lines at the top and the bottom are feathers. The bottom feathers represents the youngest person in this group, the youngest value, the lowest value, which was 18. And the top feather represents the oldest value, which was 97. Okay, and the bottom of this box is the 25th percentile. So I'm just going to look over there a little bit. It looks like that would be about 38 or something like that. So 25% of the people are below 38. So another 25 are between the median, this solid bar is not the average, it's the median, the middle value. That's the 50th percentile. So half of the people are above 50, and the other half are under 50. Okay, and 25%, the second quartile, the second 25% are between 38 and 50. And between 50 and 62, it looks like, are the third quartile, or 50% to the 75th percentile. And then 75th percentile to the end is the 298 is the fourth quartile, right? For the top 25%. So basically I can get a feel for how this is distributed and if it's normally distributed by looking at this. Now, if this black bar had been over here down towards the bottom, then I know that this would have been skewed. In other words, the median is here, but there's a lot of older people in here. So the mean is being pulled away from the median. And the way you identify which direction the skew is which way the mean is pulled from the median. So if you have a relatively normal distribution, but then you add some people that have a very high value, a large age, high blood pressure, so on and so forth, much higher than everybody else, much higher than most other people. If you get some of those, the average goes up, but the median doesn't change much. Middle value stays pretty static. The average can get pulled away very easily by high values or low values. So if you have outliers that are high, it pulls the average to the right skewed or positively skewed. If uh, um, uh, uh, you have values that are unusually low, like say birth weights, premature baby birth weights, or something like that. That would pull the average weight away from the middle weight lower. That would be left skewed or negatively skewed. Okay, so that's how we would use this. So that's pretty interesting, right? This is not that hard yet. Okay, so I want to demonstrate one other thing here, and that is that, for instance, we might be interested in comparing in this survey if the ages of the males are the same as the ages of the females in this population, in this sample. In other words, that we wind up with very young females and old males. Or what's the average age and the distribution of the ages for females and males? Well, when I did this, analyze descriptive statistics and explore, when I did it like that, all it gave me was all of the ages averaged together. It would be nice to be able to break those ages up into two groups, male and female. In math, when we break things up, for instance, if I take the number 30 and break it up into 5 times 6, what am I doing? I'm factoring it, right? I'm factoring 30 into 5, the two numbers that multiply together, 5 times 6. I can factor it again, 5 times 3 times 2, right? I'm breaking up that number, I'm factoring it into different groups. So the factor list is how you're going to break up the numerical variable age. So if I want to break up the numerical variable age into different groups according to sex, I would move sex or gender into the factor list. I haven't changed anything here at all. I still have the statistics are set up the same way. The plots are set up the same way. All I did was move sex or gender into the factor list. I'm going to click OK and let's see what happens. Okay, let's see what we get here. Oh, well, okay. Now look at the descriptors that I get here. I get I get a different average age for males and females. His female average age is 48.1. Male average age is 49.79. So the males in this sample appear to be on the average older than the females. How about the variability? Standard deviation for females is 17.4. For males is where is it? Standard deviation 17.6. Pretty similar, right? Maybe a little bit more variability, but pretty similar. So so it actually broke these people up into two groups by their gender, and it created two groups of statistics. So now I can compare the two groups to see if I see differences or similarities. Okay, what about histograms? Produce one histogram for females, and it produces a separate histogram for males. Same thing with the charts. Now, one thing that's really nice about this is it will produce box plots, but instead of producing them separately, like the histograms, it actually produces them on the same number scale. It produces them side by side like this. So I can see visually that the median age for males is a little bit older than the median age for females. But otherwise, the variability looks the same. The range looks pretty much the same, right? So it looks like there really isn't a whole lot of difference in terms of the ages of males and females in this particular sample. So this is really informative. If we're comparing say results of blood pressure tests before and after somebody took a medication, or based on whether they got the medication or placebo. It's valuable to be able to see these side by side to see if there's an average difference in their blood pressure, depending on whether they saw that they took the placebo or took the drug that you're testing, or whether the result of grades on an exam are affected by having taken a refresher class or not having taken a refresher class. In other words, you can compare two groups to each other. How did we get to that? We went to analyze, descriptive statistics, and we went to explore, not descriptive, to explore, and then we moved what we wanted in there. Do we have another nominal variable we could use? Let's try borough. Let's move borough into the factor list. Now it's going to break up all the people's ages into 5 groups and analyze each of the 5 groups. Bingo. Here we go. So 47.1 for Manhattan. Again, we don't really know if that's really Manhattan. 46.1. Oh, look at this one. 52.7. Quite a bit different. 48.97. 51.98. We're going to be using this database later on in the semester, so we're going to get a chance to see who are these where do these old geezers live? Where do you think that might be? Think it might be Manhattan? I think it most Queens. You think? Well, the average age for whatever this is for this group is quite a bit older than the others. The others 48, 47. This one is 52. Should be. We'll see. We'll see if that. Now you have a preconceived notion that the average age is the same in all 5 boroughs. But later on, when we look at this data, maybe we'll be able to make a better judgment about it. That's why we're taking statistics, to turn our notion, to abandon our notion or our preconceived notions about what this data means into what the data really represents, what the data really demonstrates. Let's take a look at those box plots, which are very interesting again. Okay, it's nice because they're side by side, and you can see this particular borough, the median age is quite a bit older than the other boroughs, right? The variability is about the same in all of them, but this one, these guys, look at that. The interquartile range, the 25th to the 76th percentile, is also different than the others as well. So we'll see what that number really, whatever number that was, we'll see what that really represents later on. So again, you can click into this, copy, paste it into a Word document. You can paste it into a report. Notice it says borough of residence down there because it says borough of residence because we changed the label, and it says Manhattan, Queens, Bronx because we changed the 1, 2, and 3 in the variable view to let SPSS know what 1, 2, and 3, and 4, and 5 represented, and age is represented here, right? So it's pretty interesting. So that's as far as we need to go in SPSS. Right? So if you can do this, you will be able to deal with anything that's on the test that will ask you, as far as SPSS, anything you'll be asked to do on the first exam. So I'm going to close this stuff out now. Nope. So how are you guys? Doing online there? Okay, are you guys okay with that? You have any questions before I completely close this down? Okay. I'm going to take a 5-minute break just to get a drink, catch up on my voice, get my voice together and stuff, and get a little bit organized. And I'm going to pause the recording, and then let's take a 5-minute break, and let's come back at 6:45, 6:39 now. Let's come back at 6:45. Okay, good. Yeah, thanks for telling me that. Matter of fact, I'm gonna step. I know that you guys probably don't want to hear this, but I know there's gonna be people online that are gonna like be missing this part. So I'm gonna step back a little bit. I'm gonna go through it pretty quickly though. Okay. Let me just. I apologize, but thank you for telling me that though, because then people would have gone nuts on I would have got a lot of angry emails. Okay, so at any rate, so let me step back over this. We randomly selected 1,200 people from this population, and we organized this data into this table that we call a crosstab or a contingency table, right? So the rows represent results of the diagnostic test for cooties. Cooties is an imaginary disease, so the rows represent people that tested positive for cooties are in the top row. People that tested negative for cooties are in the bottom row. Actually, tell you the truth, it's probably good that I'm going back over this because give me a chance to review one other thing that I kind of skipped over. In the columns are people that have cooties, that actually have the disease. Could have been diabetes, could have been any disease. We made up this fake one. Okay, and the other column is people that do not have the disease, right? Now, people who have the disease, there's 150 of them total. Some of them were correctly identified by this diagnostic test. In other words, this 105, I'm going to do this over here. This 105, that 105 represents true positives. People that are positive, that tested positive and actually have the disease. The people in the 45 that's right below that, they have the disease, but they tested negative. So they are false negatives. And then going over to the second column, people that don't have cooties. Well, they tested positive. So these people don't have the disease, but they tested positive anyway. Those are false positives, right? Positive tests, but don't have the disease. And these people on the bottom here are true negatives, right? They don't have the disease and they tested negative, right? The test worked correctly. So the first thing I might be interested in is, well, how many people in this population have this disease? Well, the prevalence is going to be equal to the number of people in the population who have the disease over the total population. In other words, 150 out of 1,200, or about 12.5% of the population, 0.125. So I'm going to go a little bit further here, and I'm going to take a look at how good is this test at predicting whether a person that has cooties, these 150 people that have cooties, at identifying them, screening them, and saying they have cooties. Well, it got the test right for this group, people who have cooties. It got it right 105 times, but it missed 45 people. So the sensitivity of the test is how good it is at getting it right, identifying people who have the disease. So that's equal to 105 times it got it right out of 150 people who have the disease. So the sensitivity is 70%. 70% of the time it correctly identifies people who have cooties. Well, how about the specificity? Well, the specificity is the same kind of idea, except it tells us how good is it at identifying people who don't have the disease. In other words, how good is it those true negatives? Okay, so it got it right. It identified people who don't have cooties. It got it right 945 times out of 1,050 times, because that's the number of people that don't have cooties. So it's equal to 945 over 1,050. Okay, so there is the percentage that I got it, that this test got it right if you don't have it. So 90% of the time, if you test negative, you don't have cooties, right? It's 90. The specificity is 90%. The sensitivity is 70%. Okay, so if I go across here, I can say to myself, well, gee, that's very interesting. What else can I tease out of here? Well, let's see. How many people tested positive? How many people actually tested positive here? Well, we have 210 people tested positive. How many people? How many? Let me just put this. I'm going to say tested positive. Okay. How many people are truly have the disease? Are true positives? How many people is that? Well, that's 105. So out of the 210 people that tested positive, only 105 of them actually have the disease. So we can come up with something called a positive predictive value. How good is a positive test at telling you have the disease? Well, let's see. You got it right 105 times out of 210 people who tested positive. So the positive predictive value is 50%. In other words, if you test positive, you will only have the disease 50% of the time. So what are they doing? This is a common screening test, would work like this. What do they do then? They send you on for a more elaborate test. So we've screened out 945 people, 990 people, and identified them presumably as not having the disease, right? We correctly 945 times, incorrectly 45 times accidentally. But we screened out a lot of people. But now that we're down to 210, we know only half of them have the disease. So there are a lot of diagnostic tests like this. You get a diagnosis, the test is positive, the doctor says, okay, now we're going to do this other more elaborate test or a gold standard test, and so on and so forth. An example of that might be a cardiac stress test. Okay, they would do a cardiac stress test, see how your heart responds to physical stress, and so on, and watch it, its electrical output, and so on and so forth, your heart rate, blood pressure, and so on. They'd put all that information together and predict whether you have coronary artery disease, right? And that the results of that test might have a sensitivity of, let's say, 80%, right? So now the 20% of the people, now let's say that you tested positive, that based on your stress test, they think you may have coronary artery disease. Well, it's not a definitive test. There are a lot of false positives in this test, especially we're going to talk about the effect of prevalence on a diagnostic test. So what happens now? What happens now is they may send you for a more elaborate test. They have a nuclear stress test that they can do, which is very expensive, but is more definitive. And then finally, the gold standard is an angiogram where they pump a dye into they run a catheter up through your artery from your leg into your heart and release a dye, and they look at this radioactive dye or this opaque dye as it goes through your arteries supplying your heart, so they can see whether the flow is good or not, right? But that's number one. That's a dangerous test. It's an invasive test. There are a certain amount of complications with it. The other test is very expensive, and so on and so forth. So the point here is that they do this screening test, even though they know there's going to be a lot of false positives, because at least they reduce the number of people they would send on for the next test. And hopefully they don't miss too many other people in the process. That's what the specificity is about. Okay, so the positive predictive value is 0.5. You can also calculate something called a negative predictive value. How good is it at predicting somebody? How good is a negative result at telling you you don't have the disease? Well, how many people don't have the disease here? Let's see. 940, 1,050 people do not have the disease. How many people tested negative? Okay, I'm going to do that over here. Let me move this over a little bit. Okay, I'll say, I'm running out of space here. Okay, I'm going to go in here and say test negative, and I'm going to go over here and say true negatives. Okay, how many people actually tested negative? 990 people tested negative. Out of those 990. Out of those 990 people who tested negative, how many of them really don't have cooties? 945 don't have cooties. Correctly were identified as not having cooties. So what's our negative predictive value? Our negative predictive value is equal to 945 over 990, which is 95%. Now, I know what happened before was you looked at, Angelia, you looked at the 105 and the 1050, and you noticed that it was 10%, right? What we really want to know is out of the total number of negative results, how many of them are really truly negatives, people that don't have cooties, right? So it's 945 over 990. Maybe I can make up some sort of chart that shows, like for instance, the way we do specificity. If you can imagine that this is true positive, false positive, true negative, and this over here is equal to true positives plus false positives. And this over here is equal to false negatives. Oops. Oh, you want to know something? I got to put a space in front of it because it thinks it's a calculation. Space equals false negatives plus true negatives. In other words, all the negatives. Well, then the positive predictive value is equal to the true positives. I got to put space again. True positives divided by the true positives plus the false positives. In other words, this number and this number, this number and this numbers. What's that? Oh, yeah, I'm sorry. I meant, let me get that out of there. Okay, let me put it over here. Okay, it's equal to uh, the true positives over the total number of positives. This is actually really should even have a parentheses in there, right? Because you got to add them together first. Total positive tests. And the negative predictive value is equal to the true negatives divided by the false negatives plus the true negatives, right? Which is, where are them? This one is the false negatives. This one is the true negatives. This is the false negatives plus the true negatives. And we just take the true negatives, which is 945, and like here, and divide it by the total, the 990, which is the total of the false negatives and the true negatives, and put it over here. So maybe this layout here will help you out. Hopefully it won't confuse you more than you're already confused. Does that help? Does it make that a little clearer for you guys online? Yes. Okay, good. Yes, so you can kind of use that table. That table is the same thing as this table. Where'd it go? Right? Those are the same as that. And if you kind of stick to this, you'll be able to figure it out. Like this part over here, the true positives, false positives, is this cell over here, which is this cell over here. Okay, so now I'm going to do this same thing. I'm going to copy and paste this. I'm going to put this over here. Okay, except this time I'm going to change something. I'm going to say that instead of 150 people having cooties, okay, I'm going to get rid of this. I'm going to get rid of this. Get rid of this. Get rid of this. And get rid of these totals. I'm going to say in this population, I'm going to say that only, I'm going to need a nice round number. I'm going to say 12 people out of 1,200. Out of 1,200, that would leave how many people that don't have cooties? That would leave 1,188, right? Okay, so out in this population, I have 12 people who have cooties, and I have 1,188 who do not have cooties, right? Okay, so I'm going to say to myself now, okay, so what have I changed here? I've changed the prevalence. So what is the prevalence in this new population? The prevalence is equal to 12 out of 1,200. That's 1%. Only 1% of the population of this population has cooties, right? So I'm going to say the sensitivity and the specificity is the same. It's the same test. The sensitivity and specificity does not change. It's a test. It's good if it's good for this population. It's good for the other. It performs the same in both populations. 0.7, 70%, and 90%. 0.9, 90%. That's the sensitivity and specificity. They haven't changed. The only thing that's changed is the prevalence. Okay, well, let's figure out what these numbers would be. If we have 12 people who have cooties and the test is 70% accurate, how many people would correctly be identified as having cooties? Well, it's going to be equal to 12 times 0.7. Now, it happens that it doesn't come out to be a round number. Trust me, we'll just work with it this way. I don't want to kill a lot of time trying to make it come out round numbers. So 70% of the time, it would be right. It would get it right. So about 8 or 9 people would test positive. How many people would test negative? Well, the difference, right? It's going to be equal to 12 minus whatever's in here, right? That's how many people it misses. 70% of the time, it gets it right. Tests them, it identifies them as positive, and 30% of the time, it gets it wrong. Now, let's go to the next step. What about negative? 90% of the time it gets it right, identifies people who don't have cooties. In this box, this is people who don't have cooties and are properly identified as being negative. Those are the true negatives. So that's equal to, well, how many people don't have cooties? 1188 times how good the test is at identifying them, which is 0.9. Okay, so 1,069 out of 1,188 people, it properly identifies them as not having cooties. How many people does it incorrectly test positive that don't have cooties? Well, that's equal to, let's see, how am I going to figure that out? That's equal to the difference between number of people who have cooties minus the number of people that assume number of people who don't have cooties minus the number of people that are correctly identified as not having cooties. So we get 118 people that it says it's positive, but don't actually have cooties, right? So, gee, this is interesting. Now, so now let's add up how many people tested positive. Equals, I'm going to round off the numbers here just to make it easier. 119 and 8 is 127. 119 and 8 is 126. 126 people tested positive. Okay. And how many people tested negative? It's equal to this plus this. Okay. As it comes out to 172. I'll call that 173. Okay. So now, notice the only thing that changed here was the prevalence. I still use the same sensitivity and the same specificity. What happens if I calculate my positive predictive value now? Okay, let's see what it's going to be. It's going to be equal to, the total, it's going to be equal to the number of people that have cooties, which is 8.4, divided by the total number of people that test positive. True positives over true positives plus false positives. That's false positives here, right? Is going to be this number. And what does the positive predictive value come out to be? Comes out to be less than 7%. If you test positive in this population, even though the sensitivity of test is 70%, specificity is 90%. If you test positive in this population, there's only a 7% chance that you actually have the disease. If the prevalence goes down, the positive predictive value goes down with it. Why? Because you get a lot of people being tested that do not have the disease. Up here, when we did this, we were only testing 945 people that didn't have the disease. Now we're testing more people that don't have the disease because the prevalence is lower, right? So you're going to wind up with more positives. And as the prevalence goes down, you got fewer people that have the disease, so you got fewer true positives. So you got more false positives, fewer true positives, so you wind up with a lower predictive value. Okay, so almost always, I don't know about this version of the test, almost always this question, even if it's not a question on the test, you should realize that as the prevalence of a as the prevalence of a disease goes down in the population, the positive predictive value for any of the diagnostic tests for it goes down dramatically. That's why when you do screenings of a large population, everybody, when you decide, well, we're going to do screenings, breast cancer screenings for mammograms for all women over 40. Well, breast cancer in women over 40 is relatively low prevalence. I mean, it's a problem when it occurs, but not many women over 40 have breast cancer. The prevalence is low. But if you test everybody, then you're going to have a lot of people that are negative that wind up because of the sensitive, depending on the sensitivity of the screening test, that are going to wind up as false positives because it's such a low prevalence. And since they get a false positive, then they have to go on for more invasive or expensive testing, lumpectomies, biopsies, and so on and so forth, to confirm whether or not they have breast cancer, right? Or for males, the PSA, protein-specific antigen, for when they use that mass test, almost all males over 50 years old nowadays, the prevalence, the number of people in the population that at that moment have prostate cancer is relatively low, a low prevalence. But when you test everybody, even if it's a relatively sensitive test, you're going to get a lot of false positives, and that winds up being an issue because you get more invasive testing and stuff. You guys okay with that? Makes sense to you? Give me a thumbs up or something. It's too bad we don't have like you know, on like Facebook, get a thumbs up or something like that, or on Twitter. Redo positive predictive value. Oh no. Okay. I'm going to go back here, positive predictive value. Okay, so here's my cooties, my test for cooties. Okay, so if I look at this, if I can see here that the sensitivity of my test is 70%. How do I know that? I know that because of 150 people who have cooties. This is the total number of people that have cooties. This is the total number of people in its population that don't have cooties, and this is the total number of people overall, 1,200. Okay, so if I have a test that's 70% correct at identifying people who have cooties, in other words, sensitivity is 70%, then 70% of the time it will get it right for these 150 people. 70% of 150 is 105. Okay. Now, on the other hand, I have a lot of people in this population that don't have cooties. In fact, I have 1,050. The test that I'm using to confirm whether they have it or not, has a specificity of 90%. In other words, for these people who don't have cooties, it's going to get correctly identify them as not having the disease 90% of the time. 90% of 1,050 is 945. That means the other 10% of the people that don't have the disease are going to be incorrectly told that they have the disease, that they test positive, even though they don't have the disease. So I wind up with 210 people who tested positive. 105 of them tested positive because they really have the disease. Another 105 tested positive because they were false positives. The test didn't catch them. It's only 90% effective, and it thinks that they had the disease. So 210 people tested positive. Of those 210 people that tested positive, right? Everybody in this row tested positive. The total number tested positive was 210. Of those 210, only 105 of them really had the disease, the ones in this column here. So the positive predictive value of this test is 105, the true positives, divided by 210, all of the positives, true positives and false positives added together. Okay? All right, good. Let's move on from there. Next thing, binomial distribution. I know this has caused a headache for some of you guys. Okay, so I have a few examples of this. And where did this binomial distribution, why did this come up? Why is this headache annoying us? And this is something that you're really going to want to be able to use Excel for, not Excel for, because it's really simpler to deal with this in Excel than to try and calculate this because of the factorials and the exponents and so on and so forth that are in the formula that you would otherwise happen to have to use. Let me open up a fresh sheet. No, I don't want to do that. I don't want to do a sheet. Okay, let me make it a little bit smaller. I can work with it. Oops, I should change the size first. Good. So we should be able to see this now. Okay, so how does this work? Well, you guys remember when we talked about situations where we randomly selected people from a population and we looked for some dichotomous variables, such as, not even dichotomous variable, yeah, but usually dichotomous variable. And we look at some dichotomous variable like, are you insured or not insured, right? Let's say I'm looking for that. Let's say in this population, in New York City today, 80% of the people are insured, 0.80. 80% of the people in New York City are insured. Well, if I ask you, what's the probability of if you, let me step back from that 1 second. Let's say that I flipped a coin 3 times. Each time I flipped a coin, the probability of getting heads is 1/2. Get heads, I could get tails, right? So now that's interesting enough, but What if I ask you, what's the probability of getting 5 heads in a row? Well, probability of getting the first one is 50%. Probability of getting the second one is 50%. Next one 50%. Next one 50%. Next one 50%. The coin, the probabilities are independent. The coin does not know what the last coin value was. So the probability of getting 5 heads in a row is equal to 0.5 or 1/2 times 0.5 times 0.5 times 0.5 times 0.5 is about 3%, right? Probability of that occurring is about 3%. Well, I can use this for other things too. For instance, what's the probability if the probability of being insured in New York is 80%? What's the probability that I pick out 4 people on the street randomly, right? Randomly select 4 people from New York, and all 4 of them are insured. They don't know each other, independent random sample. They're independent, they're not married or anything like that. They're not working at the same place, just a random sample. What's the probability that all 4 of them would have insurance? Well, that's going to be equal to the same deal. 0.8 is probability for the first person times 0.8 times 0.8 times 0.8. What's the probability all 4 of them being insured? It's going to be about 41%. Pretty good probability, right? But then it's because the probability of any one of them being insured is 80%. Now, what's the probability that they're not insured? Probability that they're not insured is 20%. 80% chance they're insured means 20% they're not insured. What's the probability I would pick out 4 people at random and none of them are insured? They're all uninsured. Well, that's going to be equal to 0.2 times 0.2 times 0.2 times 0.2 times 0.2. Okay, what is that? That's less than 1/10 of 1%. That's about 1/10 of 1%. So that's an unusual. Well, it's because it's only 0.2%, right? Now, the thing here is that this happens because they're random and they're independent, like a coin flip, right? If there is some hidden bias in here, like the random people, for instance, if I picked out 4 people and it turns out that they're related or they work for the same company, I happen to pick them out, they all work for the same company, well, maybe that company gives out insurance. So they're all insured. It's more likely that they're insured because they work for a large company, right? And maybe because of some way that I sample, that I happen to sample only at lunchtime outside of a big factory, I might wind up only getting people that are getting a higher percentage than 80% that's insured, even though the general population is 80%. That's biased, right? So in other words, if I were to ask you, um, 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 if I took repeated samples of size 8, what percentage of the time would you expect? What would you expect to be the average percentage of the time that you would get 4 people that are insured? And it should come out to this 41%. It should come out to be roughly 41%, just as we described here. What if you did that? You took 1,000 samples of 4 people, and it came out to be 52%. What would that tell you? That tells you that your samples were probably not independent because they should average, if you take enough samples to average out to average out to eliminate as much chance involved as possible, as much error as possible, then you would expect you would get very close to what you would predict for an independent sample. So that would suggest to you maybe this is not a random sample, right? So you might see it. I think on one of the homeworks you saw kind of a question like that, where it asks you something like this: what does it mean if you take repeated samples, and instead of coming out to be 25% of the time you get all 3 people are this, it comes out to be 42%. Well, the reason for that is that then probably there's something wrong with sampling. It's either not independent or not random, right? So you would expect to see that kind of result. Okay, so let's take a look at where does a binomial distribution come into this? Well, this is pretty straightforward when you're looking for all 3 people, all 5 people, all 10 people when you do a sample. meet this condition. But what if I told you that you randomly sampled 5 people and you want to know what's the probability that 2 of them have insurance? That gets very complicated now because you could have 5 people. The first person might not have insurance, second person might, third person might, fourth. There's many different ways, combinations of those 5 people where you could get 2 out of 5 people that have insurance. So instead of being a simple situation where you can just multiply it, well, now it becomes much more complicated. Okay, the probabilities become much more complicated. But we understand that, and we demonstrated this using a probability tree. You can analyze using a probability tree all of the different possible outcomes that you might have. But to do that for 3 coins, remember we did that with heads or tails for 3 coins, we filled up a piece of paper. To do that for 10 people having diabetes or not having diabetes, that would fill up 10 pieces of paper, right? It got very complicated by the time we got to all the possible permutations of who has the diabetes and who doesn't have diabetes, right? So instead, we have a mathematical formula which describes to us these probabilities based on certain starting points, based on whether or not each selection is a success, what the sample size was, what our sample size was, and what our probability at random for the entire population is. Okay, and sample size, we give that a special name. You'll see that in a second. By success, we mean if we randomly sample 10 people and we ask them if they have diabetes, then in the case of looking for people with diabetes, the success is anybody who says yes. So we might get 1 success, 3 successes, no successes. That's the number of people who don't have diabetes. The sample size would be the number of people that we're selecting, 10. And if we did it, repeat 10 people, then repeat it for 10 people, repeat it. So the sample size is each group that we're looking for a number of successes. And the probability is the probability of any person in the population that we're randomly sampling having diabetes. In other words, the prevalence. So for diabetes, it might be 10% in this population. So how do we combine this to make predictions? Well, let's take a look. Let's take a look right here. If only 55% of kids can secure an A grade in a paper, find the probability that at most 22 out of 1,010 kids are, that one's a little complicated. Let's stay with. Let me do the one I was just doing first. Let's say that I'm going to sample 10 randomly selected people. What's the probability of having diabetes in this population is 10%. What's the probability? I'm going to sample 10 people. What's the probability that 2 out of the 10 have diabetes? Okay, so I can use something called a binomial distribution, a representation of an Excel of that formula. I'm going to type equals binomial distribution, and I'm going to hit the open parentheses. As soon as I hit the open parentheses, I see it asks me for number S, number of successes. Okay, I'll wait for you guys to catch up to me. Binom, B-I-N-O-M, D-I-S-T, and then put in open parentheses, equal binom dist, open parentheses. And when you finish with when you put the open parentheses, it should prompt you at the bottom there for what it wants next. You got that? Okay. So now what's it want first? It wants the number of successes. That's 2. We're looking for 2 out of 10, right? Number of successes. Number of trials is the sample size, 10. Put a comma in between each. 2, comma, 10. What's the probability of success for any individual in the population? In our case, it's comma and then 0.1. And then finally, cumulative. Okay, well now here's where understanding the question is important. Did I ask you what's the probability of exactly 2 people in this population? What's the probability of at least 2, less than 2, so on and so forth? Let's say I asked you what's the probability exactly 2 have diabetes. I would type in here false for cumulative because I only want the answer for exactly 2, and I hit enter. And the probability turns out to be about 19%. Okay, what if I had asked you what's the probability for 2 or fewer people having diabetes if I randomly sampled them? Equals binom dist. Good work, Angelina. Binom dist, parentheses. Well, now it's still 2, right? Number of successes, 2 or less. Trials is 10, still, comma. Probability hasn't changed, it's 0.1, comma, except this time I'm going to say true. And what it's going to do, it's going to take the probability for 2 out of 10, 1 out of 10, and 0 out of 10. Don't forget 0 out of 10 could happen too. And add all those probabilities together to tell me the probability that 2 or fewer, 2, 1, or 0 out of 10 have diabetes. And that's 93%. 93% of the time, I would expect that 2 or fewer out of 10 would have diabetes. Okay. What if I asked you, what's the probability of 3 or more people having diabetes? Well, hang on a second. Problem here is that this only works for true or false for cumulative. False means it's only going to give me one number, probability for one number. True means it's going to give me the probability for that number and everything below it. But now I'm asking, what's the probability 3 or more? In other words, more than 2 people out of 10. What's that probability of that happening? Well, the probability of that happening is going to be probability of 2 or fewer, whatever's left from 1. It's going to be equal to 1 minus the probability for 2 or fewer. And that gives you the probability for 3 or more, about 7%. Okay, makes sense? I'm going to move on. I'm going to do another example of this. Again, you'll be able to spend, like when I post a recording, you'll be able to go back over this and play around with it a little bit more. Okay, let's see. Let's try this one. 80% of people who purchase pet insurance are women. If 9 pet insurance owners are randomly selected, find the probability that at least 6 of them are women. Okay, let's do that. So we want to know, let's say, equals binom dist, parentheses. Okay, 80% of women who purchase pet insurance are women. 9 pet. So what is? Let's see, number of successes. What's the probability? Exactly 6 of the 9 are women. So 6 is the number of successes I'm looking for, comma the number of trials. We randomly select 9 pet owners. That's the number of trials, comma, or sample size really, comma. What's the probability that anyone in the population will have pet insurance? 80% of people. It's 0.8, comma, and we want to know just 80% of people who purchase pet insurance are women. My pet insurance are women. Oh, okay. So what percentage of these women are like that? What's the probability that 6 out of 9 of these pet insurance purchasers are women? It's for any one of them, it's 80%. It's likely to be a woman. So I'm going to say false because I'm only interested in the probability for exactly 6 out of 9. And that's equal to a little under 18%. What if I ask you what's the probability for 6 or fewer women? 6 or fewer purchasers being women. That's going to be equal to the same thing. Binom dist, parentheses, 6, comma, 9, comma, 0.8, except this time I'll say true. So I get the probability for 6 or fewer. 26% for 6 or fewer. What's the probability for more than 6? For more than 6, it's going to be what's left. It's going to be equal to 1 minus 6 or fewer, which is that. What's the probability for less than 6? Equal binom dist, parentheses, less than 6. That means I'm not including 6. So it would be binom dist 5, comma, 9, comma, 0.8, comma, true, because I said less than 6 would include 5, 4, 3, 2, 1, 0. That's about 8.5%. See, a little bit tricky there. Then cumulative is true, right? Exactly. It's cumulative is true or false. Okay, so there's a lot of permutations to this. Let me see if I can't find that one. Let's try one here that's a kind of a political one. In each of the four races, Democrats have a 60% of chance of winning. So our trial size here is four races. Okay, the Democrats have a 60% chance of winning in general in these four races. Assuming that the races are independent, what's the probabilities that the Democrats will win 0, 1, 2, 3, or all four races? I'm going to do all four of those. Equals, whoops, let me get some clean area here, equals binom dist, parentheses, and what's the probability that they'll win none? 0, comma, four races, four trials, comma, and the probability is 60% of winning, comma, I'm going to type in true. It's whether I type in true or false here, it doesn't matter because it's on 0, so it's going to give me the same result. Okay, probability of losing all four races, winning none is 2%. Well, how about winning one? Parentheses, that's going to be 1, comma, 4, comma, 0.6, comma, and that's going to be false also because I'm only looking for exactly one. And that comes out to be about 15%. What's the probability they're going to win 2 out of 4? Equals binom dist, parentheses, 3, comma, 4, comma, 0.8, 0.6, comma, false again, only exactly that, only exactly this outcome, is that, so that's the probability of winning 3 out of 4. What's the probability of winning all 4? Equals binom dist. Did I miss one here? I'll go back and I'll figure it out in a second. Binom dist 4, comma, 4, comma, 0.6, comma, true, false rather, for exactly 4. I missed one. Okay, what did I miss? This one is 0. This one is 1. I missed 2. Hang on a second. Let me insert a row here. Okay, I can get away with that. Okay, equals binom dist, parentheses, and I missed 0, 1, 2, I guess, comma, 4, comma, 0.6, comma, false. Okay, so this is the probability of getting at least, getting no wins in the four races, probability of getting 1 out of 4, 2 out of 4, 3 out of 4, and 4 out of 4. And of course, if I add all these together, it's all the possibilities I can have. So it adds up to 1. Okay. And if I wanted to know what's the probability of winning 2 or fewer, that's going to be equal to the sum of winning 2, 3, or none, 2, 1, or none, which is 52%. I could also do it this. What's that?
How come 3 and 2 are the same?
Chance. Just the way it came out. Well, if you think about it, if you think about it, 2 out of 4, they're inverses of each other, right?
Yeah,
Okay.
yeah.
3 out of 4. Yeah, I got them right there.
15%.
Yeah. Okay. So at any rate, so next, let me do this. Also take a look at this. I just said the probability of winning 2, 1, or 0, 2 or fewer races is 52%. I could have done it this way: equal binom dist, said 2 or fewer, 2, comma, 4, comma, 0.6, comma, and say true, and I should get the same result as adding up these three results gave me. And it does give me that result also. Okay? Okay, good. I think we beat that to death. Okay, and you can always go back and take a look at this again as well when we get the recording posted. Venn diagrams. I want to go quickly over Venn diagrams. Okay, how much time we got here? 40. I think we're doing okay. Okay. I kind of set this up ahead of time, so I wouldn't have to kill too much time. Okay, so let's see what we got here. I know these things are ugly. Right? We kind of went over these when we went into probabilities. The first thing I want you to remember is that, let me get the tablet plugged in here. First thing I want you to remember is that when I describe Venn diagrams, okay, it's turned on. I think it's turned on. First thing I want you to remember is when I use union and I use intersection, they mean certain things. A union B means it could be either condition satisfied, right? So A and B or A or B all satisfy that condition. A union B means either one of these or both together satisfy that condition. A intersection B means both conditions have to be satisfied. Okay? So if I asked you what is this area in here represent? A and B. Is that a union of the two of them? Union means both of them are but either or both can satisfy it. But we didn't highlight the outside, right? So you have to have people only in here that you have people only that satisfy both conditions. Keep in mind the reason why we're doing this is because it really represents a population. So for instance, A might be people who have cancer and B might be people who have heart disease. Some people have both. So they're in here. That is intersection, right? That would be the intersection of A and B would be represented here. What does that mean? That means I shouldn't put that up there. I'll put it down here. I got a reason for that. Okay, because that up there would mean a complement. In other words, not A. So A intersection B means that they have both cancer and heart disease. People over here only have cancer. People over here only have heart disease. Heart disease. Only have heart disease. People in here have both. Well, how about all of this? If I just took all of this, how would I demonstrate what that means? What is that? That's going to be A, B, right? Well, people in here have only cancer. People in here have heart disease. People in here have both. So it's really, they could be either and be included in this. That's the A union B. Okay, so we see. How about, how about, how about if I ask you what this means? Okay, what does this mean? That would just be A, right? That'd just simply be A. It's irrelevant whether they have B or not because they would be included as people who have A. Well, how about this? What would this mean? Right? Well, those are people who have A, who have cancer, but we're leaving out people who have heart disease, right? We don't want people who have heart disease, right? So this is A and intersection B prime. What does B prime represent? B prime means that they don't have B. They're not B. So the people that are in here are A, but they're also not B. Okay. I could also do this another way. I could just highlight this part over here and call this not A intersection with B. In other words, you have to satisfy both conditions. Who satisfies both conditions in an intersection, right? So people who are B, but they're also not A. So if they're A, we're leaving them out. So this is not A intersection with B, and this is A intersection with not B. Okay, a little weird, right? But I wouldn't worry about it too much. Once we get through, like once we get past this exam, I promise never to bring up Venn diagrams again for the rest of the semester. Okay, the other test is non-cumulative, so you don't have to worry about being tortured by this again. Let me move on to the next thing. Did I have a question there? Let me just check to make sure. Okay. Okay, A, B. Good. All right, good. I got the thanks there. I'm not sure if it's a thanks for not bringing this up ever again after this exam, but I can understand it would be. Okay, now let's take a look at normal distribution, at the normal distribution. Okay, and there's a couple of ways that we looked at this normal distribution. Okay, first of all, normal distribution had certain properties that we were interested in. Okay, here's a couple of them right here. I'm just going to work with this one. Okay, what are those properties that we were talking about? Okay, well, number one, it's symmetrical, right? Symmetrical, we know that the mean represents the middle, the mean and the median are equal, right? The middle value is equal, okay? And we looked at certain properties of the normal distribution. Okay, one of those was this thing that we call the empirical rule. Now, this normal distribution, it could have this shape. It could have, matter of fact, I think I got a picture here of a couple of other ones. You know what I want. Yep. Here, nope, that's not the one. There we go. Let me see if I can't open that up. Make it bigger. Without it's blurring out too much. These are all normal distributions, right? Every one of these is normal distribution. It's bell-shaped curve. It's normally distributed, symmetrical, and so on and so forth. What are the differences? The differences are where the middle is, the mean is, and how spread out they are. So this blue one has a mean of 0, right? And it has a standard deviation, a spread of 0.2, 0.4. It's narrow, it's not very widely spread out. This red one has a mean of 0 and a standard deviation of, well, it's a flatter version of this. And this green one is another example. And look at the yellow one. The yellow one has a really big, the mean is -2, the middle is -2. Doesn't look like negative. Oh, there is. The mean is 0, and the spread is 2.2. It's really flat, but look at it. It's still bell-shaped. It's still symmetrical about the middle, and it still has all the property of all these other normal distributions as well. So when we have a normal distribution, we can depend on it to exhibit certain properties. Among those is the empirical rule. And what does the empirical rule tell us? Empirical rule tells us that a normal distribution has a certain distribution of the probabilities or the outcomes that are built into it. So for instance, 68.2%, I'm going to call it 68%, of the outcomes of the population is between one standard deviation below and one standard deviation above where the mean is. Now, this works for all normal distributions because we describe the spread not in numbers, not actually in the values, but in terms of the standard deviations. So this could represent race times. And the average race time, the average half marathon time could be 112 minutes, right? And the standard deviation for the race times could be let's say 20 minutes, right? So this one standard deviation below the mean could be 92 minutes, and one standard deviation above the mean could represent 132 minutes, right? And 68% of the runners, if they're normally distributed, would fall between 92 and 132, right? And we could also say instead, let's say this represented blood pressures, and we could say that this blood pressure represents 80, right? For the runners' diastolic blood pressure is 80, right? And the standard deviation for blood pressures is 10. in which case 1 standard deviation below the mean would represent 10. It would represent 70. 1 standard deviation above would represent 90. Well, now, entirely different numbers, but the same distribution represents them when you describe it in terms of standard deviations. In other words, 68% of the runner's blood pressures are between 70 and 90. So we can apply this to any normal distribution, this empirical rule. And we could also go further and say 2 standard deviations below the mean and 2 above the mean represents 95% of the values. And 3 standard deviations above and below represents 99.7% of the values. So pretty interesting. There's a lot we could do with this, right? So I'm going to go ahead and I'm going to apply these to, I think I got a problem or two. I'm not sure. Let's see. Did I make a problem up? I guess I didn't make a problem. I'll have to make it up on the fly. Okay, so for instance, if I were to ask you, I'm going to take the blood pressure example. Mean blood pressure, the mean blood pressure is 80, and the standard deviation of blood pressures is equal to 10. If I were to ask you, what percentage of this population had a blood pressure between 70 and 90? What would you tell me? Well, how many standard deviations are there between 70 and 90? 70 is one below. 90 is 1 standard deviation above, because standard deviation is 10. So what percentage of this population? 68%. What percentage of this population would have a blood pressure between 60 and 100? Okay, what do you think? Right? Well, that would be 2 standard deviations below and 2 standard deviations. Oh, exactly, 95%. What percentage of this population would have a blood pressure less than 60? Okay, less than 60, less than 2 standard deviations below. Right? What percentage of the population would be in here? Okay. Anybody want to hazard again? Yeah, 2.5%. How do we get 2.5%? Because 95% is between 2 standard deviations, 2 standard deviations above. We're interested in this little corner down here. There's 5% that's outside of this range, but we have 2 tails. So we have 5% left, but they're split between the upper tail and the lower tail. So this is 2.5%. Okay, so what percentage of this population is greater than 70? Okay, what do we think there? How are we going to do that? Greater than 70 would represent all of this, the whole upper part from this point on. Okay. Well, we know that the mean. First of all, if I could actually, if this is 68%, then from the mean to the -1 is 34%. From the mean to +1 standard deviation is 34%, right? So really the mean on up represents 50% plus 34%. So 84% of the population is above a blood pressure of 70, right? See how I did that? Right? I kind of broke this down. Well, this is 34%. And what is that? If this is 34 and 34%, if I ask you what percentage is less than 70, right? That should be pretty easy to do because I know that, gee, less than 70. Well, if this part is 84%, then this part has to be below is 16%. Similarly, if I asked you what percentage was between, let me think here, between 60, let me think about this a second. What percentage of this population is greater than 60, but less than 70? Between 60 and 70. Well, 60 is 1 standard deviation below the mean. 60 is 2 standard deviations below the mean. 70 is 1 standard deviation below the mean. So if I look at one standard deviation below the mean, that would represent 16%. But then if I look at the proportion that I'm not including because I'm stopping at 70, that means I'm getting rid of the 2.5% here. So this area in here is going to be equal to 16% minus 2.5%, right? So it's going to leave me with 13.5%. These are all rough numbers. This is not, the empirical rule is not an exact measurement. I'm going to leave it at that so you can go back and play with it a little bit and review it, from the recording. But you can get quite a bit of information from the empirical rule. And if nothing else, it'll help you visualize what areas, what probabilities, what percentages of these populations are represented by the areas that you're looking at in terms of your probabilities. That'll help when you're doing it from a table or from a program to be able to visualize this using the empirical rule and get an idea of what it might be approximately so that it's less likely you'll get it wrong when you try and actually do the calculations a little bit more accurately, which I'm going to do right now. Okay, so I'm going to look at how to do this more precisely. Okay, so now I'm going to give you another example. I'm going to say, let's say that the mean for my population, U for my population, is equal to 100. And the standard deviation is equal to 20. Okay, well, if I use the empirical rule and I ask you what percentage of this population is going to be under 60, right? Less than 60, that's 40, that's two standard deviations below. That would be about 2.5%. It would be the very end down there, would be the bottom 2.5%, right? That's what we would guess. Well, let's do this more accurately. Let's actually use the table to figure that out. Okay, so mean is equal to 100, standard deviation is equal to 20. How many standard deviations is this? Well, the standard deviation is equal to 2. We're going to define that as the z-score. We're going to call that the z-score. The z-score, if you don't want to when you're dealing with not round numbers, it's going to be easier to just use a formula and say, whatever the value you're interested in, we'll call it x, minus the mean over the standard deviation is the number of standard deviations. Okay, so z is equal to 60 minus 100 over 20. Okay, that's negative 40 over 20 is negative 2, which is exactly what we figured before. Let's go to our z table. And I'm going to go to my Agresti z table. I don't know if I put one on black. It's in one of the previous sessions in case you don't have it handy. But you can also just look over my shoulder for the time being. Here's a z table. What is the area to the left of a value of negative 2 for z? What area does that represent? Negative 2? Well, that's 0.0228. Move this out of the way. So this area, the z-score of negative 2, this area represents 0.0228. Well, if I use the empirical rule, it would have been 0.0250, right? 2.5%. It's not. It's more accurately that number. If I asked you, what's the percentage of this population? Or in other words, what's the probability of me randomly selecting a person from this population who has a blood pressure greater than 60? Well, it would be everybody that's not under 60, right? It would be everybody to the right of this, which would be the remainder of this population, which is going to be 1 minus 0.0228, right? Which is going to be 0.9772. 97.72% of the population is above, or probability of selecting someone is 97.72. So what about if I make this a little bit more complicated? Let me start with fresh sheet. Okay. Okay, so let's say I told you that the mean was equal, for this population is equal to 150, and the standard deviation is 10. Okay, what if I were to ask you, what's the probability that you would have that if you randomly selected someone from this population, that they would have say it's weight. Let's say that their weight is less than 137. Less than 137, eh? Okay. So I can't use the empirical formula because it's more than one standard deviation below, but less than 2. So let me find a z-score. What's his number of standard deviations that this represents? So it's going to be 137 minus 150, x minus mu, standard deviation, over 10. That's 13 over 10 is equal to 1.3. So what's the likelihood that you'd pick someone that had a weight on less than 137? That's the standard. That's 1.3 is the z-score, right? Z. Okay. So what is the probability? What is the area of the distribution here? Let's go to our table. Okay. Negative 1.3 represents an area 1.30 of 9.68%. 9.68%. Get this out of the way here. So this is 9.68%, or in other words, 0.0968 is what this is. Okay. Well, what's the probability of selecting someone from this population that has a weight that's greater than 164? Well, that z-score for that is going to be equal to 164 minus 150 over 10 is going to be 1.4. So we're looking for the area above a z-score of plus 1.4. Let me put the minus sign in there so I remember. Above 1.4. So what is that area? Well, if I go to my table, I'm going to look up an area for a z-score of plus 1.4. Now you'll notice that you have to scoot up to the next chart. And plus 1.40 represents an area of 91.9192. Well, what does that area represent? If you look at the chart, the description on the chart, it represents the area from that z-score down. Notice that anytime you have a positive z-score, the area from that point down is going to be more than 50% because it's going to be to the right of the mean. So what is that area? It's 9192, yes. 9192. I almost got the whole night without forgetting a number. 0.9192? Okay. The area is 9192, but it's not this area. That's the area from here down. So what is this area? It's 1 minus that, what's left, right? So 1.000 and 0, and I'm going to subtract 0.9192, and we got 8, 0, carried 1, 9, 0.9. Is that right? Yeah. That's going to be 9.0908, right? Or 9.08%, 0.0908. That's what that area represents. So what if I ask you, what is the probability of picking someone who is less than 137 or greater than 164? Well, that would be the sum of this area and this area. So I would just add this number and this number together and find out it's about 18%. What's the probability of randomly selecting someone who is between 137 and 164? Well, it's going to be the area in the middle here, which is going to be 100. It's going to be 1 minus each of these two numbers combined, minus 0.0968 and 0.09, excuse me, 0.09, it's 0.0968, 0.0908, right? Subtracting both of these from there, leaving about 82% to be in between these two, right? So you might wind up with a problem like that. So be careful with the way you use the table, the way you get the numbers, and the way you interpret the areas that are represented by the table. Just want to give one last thing where this table is concerned. Okay, and that is, okay, what if I were going to take the same distribution? I forgot what it was now. I think it was 100 and, what was the mean that I had there? 150?
Yeah.
And standard deviation was 10, something like that. Well, I'll work with this one. What if I were to ask you, let's say that this is weight. I think think it was 20. I don't remember. Let's call it 10. What if I were to ask you what weight represents the lowest 10% for this population? Well, the people that are the lowest, maybe I'm screening for eating disorders or something like that, and I want to know what weight value represents the point at which 10% of the population weighs less than that. So I'm looking for what this number is, what this weight is here, where this area is 10%. That's the lowest 10% of this population. Well, how am I going to figure out what that is? Okay, well, let's see. I know the mean is 150, but what is this number over here? Well, if I go over to my table, I can use it backwards. I can say, I want to know 10%. Let's see. Let me go to this negative. It's on the left side of the mean, so it's going to be on this table. What z-score represents an area where below it is 10%? So I'm going to look for 10% in this table. I see 9.34. I see 9.951. I see, I'm going to have to move this over so I can see it a little bit better. I see 10, yeah, it looks like it's this one right here. So what is the z-score that represents that 10%? It's negative 1.28. So that z-score for that value, 10% of the population, is a z-score of negative 1.28, right? That's how many standard deviations below the mean that weight has to be in order for me to have 10% to the left of it, of this distribution. Well, that's great, but it doesn't tell me what weight that represents. But I got a formula here. Z is equal to x minus mu over the standard deviation. Well, now I know what Z is. Z is 1.28, negative 1.28, is equal to, I don't know what x is. I don't know what weight that represents, minus the mean, which I know is 150, over the standard deviation, which I know is 10. So now I can say to myself, there's only one unknown here since I know what z is. So now I can actually cross multiply and say 1 times this, x minus 150, is equal to negative 12.8. And I can move the 150 over to this side. And x is going to be equal to 137.2. Right there. Carry the 1. I think that works. Yeah, that works out. So I've used the area that we were looking for to help me calculate what that weight would be. So now I know 10% of this population weighs less than 137.2 pounds. Okay, so we can use this many ways. The only last thing, we started to introduce confidence intervals and so on and so forth. I just want to mention one other thing, and that is, let's see. Let me make sure I got the right one. And then we'll call it a night. Okay, let's see. Oh, no, I don't want that one. Wrong one. This one. Okay. So if I have a normally distributed population, right, and it has a mean of 100, 130, and has a standard deviation of 10. If I take repeated samples from this population of, say, sample size equals, I don't know, let's call it 100. Okay? If I repeatedly take samples of size 100 from this population, each time I do that, I'm going to get an average I'm going to take 100 people, randomly select from this population, measure their weight. The first time I do it, I get 128. As it happens, the true population average weight for the population is 130. The next time I do it, I might get 131. The next time I do it, I might get 134. Next time I do it, might get 128. If I do this many, many, many times, 1,000 times, I'll have 1,000 numbers here. The average, the new mean for all of these sample means, these are all sample means. Take 100 people, take the average. If I added all these up and divided by the number of times that I did it, it would give me an average, a new mean, which is going to be a sample mean. A mean it's going to be a mean for all of the sample means. And that mean is going to approximate the population mean. Makes sense, right? Half the time you're going to be lower, half the time you're going to be higher just by chance. It's going to average out. If you do it often enough, it's like going to the casino. If you gamble enough, they're going to win, right? Because the odds are going to come out as they will come out. So we will, if I keep doing this over and over again, I'll get a mean, and the mean of these sample means is going to approximate the mean of the population. But notice that the weights in the population, 95% of the people are between 10, one standing deviation is going to be between 110 and 150, right? So if I just sample one person, they're going to be between 110 and 150 95% of the time. But if I take a sample size of 100 and then take the average of those 100 people, they're going to be very close, much closer to the mean is. So if the population distribution looks like this, the sample distributions, the distribution of the sample means for a sample size of the 100 is going to be much narrower. It's going to be close to the population mean, but it's going to be narrower than the population is. So this is the distribution of all the possible samples that I might get. It can be much narrower distribution. The relationship here is that the standard deviation for all of these sample means is smaller the bigger the sample size is. The bigger the sample size is, the closer the number is going to be, each sample is going to be to the mean, better approximation of the mean, and the less variable they're going to be. And this standard deviation for all of these sample means taken over and over again is equal to the standard deviation for the population divided by the square root of the sample size. So what is it going to be for a sample size of 100 for this samples drawn from this population? It's going to be equal to the standard deviation of the population, which is 10, divided by the square root of the sample size, with square root of 100, it's going to be 10 over 10, which is equal to 1. So the standard deviation of all of these is going to be equal to 1. So if I take a sample of size 100, I would expect 95% of the sample means to be between 128 and 132. Right? Just like this. It's going to be a normal distribution just like this, except its standard deviation is 1 instead of like the population being 10. So I would expect these two standard deviations below and two standard deviations above to be 2 below 130 and 2 above 130. So my samples are going to be very much closer. Why is this important? Because we're going to learn all sorts of stuff about applying this to predict whether a sample is a good approximation of the population mean. So this has a special name. This standard deviation for repeated samples is called instead of using the word standard deviation because we use it with the population, we're going to use the word standard error of these sample means. Standard error. Okay. So the standard error for sample size 100 from this population, for the distribution of sample means from this population, is equal to 1. That's it. That's enough for tonight, I think. That'll get us started. So